Okay? So all these are always related together. And they're linear, they're just resistors. We measured them with our voltmeter, right? So you can measure them. So you just think of the meter as the resistance. Right? Now, in that problem, on that test, I had you construct we were trying to make a 1 amp meter from this 100 microamp meter. It's easier actually to look at the final application and figure out the resistances from the final. If this is going to be a 1 amp meter, that means it's going to be 1 amp full scale. What's going to be the voltage, Miguel, across that meter when it's reading 1 amp? What do we want it to be? If we're going to turn this 100 microamp meter into a 1 amp meter, what's going to be the voltage when we have 1 amp? It's going to be full scale, which is 1 volt. So if we have 1 volt and 1 amp, what is the resistance we see? 1 volt, 1 amp, 1 ohm, right? So the resistance total is easier to get because you just use the outside quantities. So this is the total resistance, and we know that R total is equal to, this is called RSH. What's the SH stand for?
Shunt.
Shunt, right? Okay, so this would be R shunt times R meter over R meter plus R shunt, just the resistor combining equation, right? What do we know about R shunt, Davis, compared to 1 ohm and compared to 10 k ohms? What's it going to be closer to?
It's small.
It's going to be real small, closer to what value? It's going to be very close to 1 ohm, right? Because what? If 1 amp's coming in here and 100 microamps is going there, that means 0.9999 amps is going that way. So it's a much smaller resistance. It turned out in calculation to be 1.0001, and it repeats ohms. But it's always a little bigger than the total, right? Because this in parallel with 10K becomes 1 ohm, right? And that's really the limiting factor on those meters, is the precision of the shunt, right? Okay? You remember we went through that whole schematic on the Simpson meter to calculate the parallel resistance and that kind of thing, right? Okay, if we're going to use this analog meter as a voltmeter, right? We want to use it on 100 volts. We're going to have to do what? We're going to have a voltage divider, because this meter is only good for 1 volt, right? Full scale. So if there's 1 volt across the meter, where's the other voltage? Across the resistor, right? What's the current flowing in the meter? Whatever the meter, yeah, if we want it to be a 100 volt meter, it'll be full scale, or 100 microamps. Anyway, 99 volts over 100 microamps turns out to be 990 k ohms, or it's 99 times this, because resistance follows voltage. More voltage, that means it's a larger resistance, right? Okay? Now, what I was trying to, on the problems, I didn't grade because I thought the questions were poorly worded, okay, by myself, so I'm embarrassed by that. I was trying to show you that that can cause errors in a circuit, right? If you have a circuit, let's say with 1 ohm and 1 ohm, right? Okay? If we tried to put our ammeter, right, in this circuit, right, our 1 amp ammeter in this circuit, is that going to cause error in our circuit? It's going to change it, right? Remember Heisenberg's measurement principle, right? Uncertainty principle of metering. Okay? Because why? What happened when we put that meter in there? We just put it in another resistor of 1 ohm. And if these values are similar to what your meter is, and that's really why we don't like analog meters anymore, because they change the measurements, right? Okay? And it works the same for the voltmeter. In this case, this was, if we were measuring a large voltage, right? So it was 1 megohm and 1 megohm. If I put this voltmeter, you know, in parallel, it would be like adding a 990 k ohm resistor in parallel, which would change it, right? Okay? Now, okay, so that's the analog meter. What about the digital meter? What's good and bad about the